Hi there, everyone. I'm going to talk today about a few things involving more advanced models of bonding, which would be back in Chapter 6, and then transition metal complexes, which I believe is Chapter 19, unless I'm mistaken. So the first thing I want to talk to you is, first of all, I'll say what we've been using is largely called valence bond theory, where we write Lewis dot structures, we predict geometries using the VSEPR model. And we've talked in that a little bit about hybrid orbitals. I just want to remind everyone that hybrid orbitals are kind of a fix. The geometry of compounds, and indeed some of the compounds they form, didn't seem very normal. For example, if you had carbon, which they have here, carbon's 1s2, 2s2, 2p2. If you wrote the electron dot structure of a carbon atom written, in that kind of way, you'd expect it to be something like that you'd find that carbon only had 2 unpaired electrons and an empty p orbital, and so the bonding would be, not what we see, which is that carbon normally forms 4 bonds. So what we say is that the 2s orbital and the 2p orbitals, that typically those hybridize into something like, maybe an sp plus the 2 p's that are left over, or sp2 plus the 1p that's left over, or sp3, which is normally what we see a lot of times with carbon compounds. And that's how we explain that. Now, these extra p orbitals here are usually involved in multiple bonds, that is to say, double or triple bonds. And what you can see, just one thing you can see, is that we have over here a picture of the electron, the electronic energy diagram here, and you have the unhybridized version over here on the left. Okay, and then your hybrid orbitals are over here on the right. And what we've said is that the S mixes with 2 p's there, you get 3 sp2s. You always get the same number of orbitals that go into the mix. And of course, we've learned that that correlates with the number of groups of electrons around the atom. And we talk about explaining how bonds form. So you have the compound ethylene here, which is written, we could write the structure like this. And what we say is going on here is that we have a sigma framework, which is formed by the sp2 orbitals interacting with either an s orbital and a hydrogen, like right here. This is sp2 from the carbon interacting with a hydrogen s orbital. And then right here in the middle, we have the 2 sp2 orbitals interacting. And we call that a sigma bond. And symbolized by that lower case sigma there. And then the 2 p orbitals that are left over, they interact and form a pi bond that has this above and below representation there. So that's a pi bond. And when you're looking at a structure like this one, one basic skill you should have is counting the number of sigma and the number of pi bonds for this compound. And it's real easy. What you have to recognize is that any bond that is a single bond, or the first bond in any multiple bond, is always going to be a sigma bond. So we have 5 sigma bonds here, and I'll leave them normal. Let me just highlight. I'll highlight the pi bond, which is one of these 2 double bonds here, is going to be our pi bond. So we have 1 pi bond present in that structure. So, give you another example that you might see, typical kind of compound putting together, probably unrealistically, some of the organic functional groups that you'll encounter next year. But this is something that contains a carboxylic acid group over on the right and a triple bond or an alkyne group over on the left. So if I had to count sigma and pi bonds in this structure, what would I get? You may want to pause the tape for a second, see if you can work that. So what I'll do is I'll highlight the ones that are pi bonds. So if you haven't paused and thought about this a second, you might want to do it. Last chance. Okay, so this triple bond here, two of those are pi bonds. The one that isn't highlighted is a sigma bond, and of course it doesn't matter which one of those I call sigma or pi. And then over here, the double bond with oxygen, there is a pi bond there. So I have 3 pi bonds in this molecule. And it's real easy to forget the hydrogen. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds. So don't forget the hydrogens. But that's a real baseline skill for that. And you'll think about those a lot in organic chemistry. Now there's another way of thinking about bonding, and this is one that's different that we haven't talked too much about. It's called molecular orbital or MO theory. And molecular orbital theory is probably a more accurate, rigorous way to describe bonding, but it's much more complicated than valence bond theory, and we'll only look at it being applied in a few cases here. But there are times when you talk about MO theory in organic chemistry and other types of chemistry. So the simple idea is that all the atomic orbitals in a molecule combine to form molecular orbitals, which may extend over the entire molecule, may not. That gets really complicated, so a lot of times we just find ourselves looking at simple systems like the homonuclear diatomics. Let's write that down. Homonuclear diatomics. Well, if you told someone you were studying homonuclear diatomics today, they'd probably be really impressed. But all that means is it's a 2-atom molecule, diatomic, and it's the same element, homonuclear, same nucleus. So H2, N2, O2, those kind of things are homonuclear diatomics. So if you look over here at the left, and again, most of the figures I'm citing today come from the textbook, so you can see where I'm getting them. Figure 5.29 here came from Chapter 5, right? So we have 2 s orbitals, and what we say happens is when those 2 orbitals combine, they can combine constructively, in which case they go down in energy and form what's called a bonding orbital. And if they combine destructively, they form an antibonding orbital, which is up in energy. And electrons that are in bonding orbitals contribute to a bond, and electrons that are in antibonding orbitals erase bonds, essentially. They subtract from bonds. So we have an equation that you'll be using. The equation talks about the bond order, which means, if it's 1, it's a single bond. If it's 2, it's a double bond. If it's 3, it's a triple bond. So what we're going to do is we're going to count the electrons in the bonding orbitals and count the electrons in the antibonding orbitals and subtract the antibonding ones from the bonding ones, and then we're going to divide by 2 because there's 2 electrons in a bond. And so one thing we'd expect to see is that we probably get a consistent bond order between most of our structures with what we would do from valence bond theory. So down here we have the MO diagram for hydrogen. You see you've got the 1 hydrogen atom over on the left, 1 hydrogen atom on the right. Orbitals overlap like they do above, and so this bonding orbital is the one that's down there. This anti-bonding orbital is the one that's up here. And since hydrogen has 2 electrons in its atomic orbitals between the two H2s, right, 1 in each one, we fill up the molecular orbitals from the bottom. We follow all the rules we followed before, you know, the off-ball principle, start at the bottom and go up. The Pauli principle, which says we have to pair electrons if they're in the same orbital. And Hund's rule, which says that if we have 2 orbitals at the same energy level or more, we put the electrons in each individual orbital without pairing them first, and then only pair them when we're forced to. So if you look at hydrogen here at H2, we get that our bond order for that is going to be 2 minus 0 divided by 2. That's 1, which is consistent, of course, with the valence bond theory depiction of hydrogen. So that works there. The next figure here shows how p orbitals on 2 different atoms, right? So these are our p orbitals here, and they can combine in a way that's constructively or in phase. Okay, so you see the blues are both on the bottom, so this is what I would say is in phase or constructive combination. That gives us a bonding pi orbital. And if they combine out of phase at the top, you get an antibonding pi orbital. Now, if you think about the way the p orbitals are oriented, you know, basically you've got one on the x, y, and z axis, and then you've got 2 atoms coming together. That means 2 of those orbitals are going to be combining in a side-to-side fashion like this. But one pair of orbitals is going to be combining in an end-to-end fashion like this one. So this is the side-to-side. And these are the end-to-end. And again, the bottom one is in phase. The top one is in phase. So that's our bonding p orbital, that our pi sigma sub p orbital, which means it's a sigma orbital formed with p atomic orbitals. And these are our antibonding sigma star p orbitals. So we would have called these are our sigma. You see down here it says sigma 1s and sigma star 1s, where sigma star 1s is the antibonding one, and sigma 1s is the bonding one formed from the atomic 1s orbitals. So one thing you see, this is looking at the 2s and 2p. So you got your sigma. It's over on the right side, but you have your sigma 2s at the bottom, your sigma star 2s there. Then next up here is the pi 2p. Then we have the sigma 2p. Then up at the top we have the pi star 2p, which we know because there are 2 of them, and the sigma star 2p is at the top. And we're looking here at the second row of the periodic table and looking at going across from lithium through neon. And what happens is, as the atomic number increases, the orbitals are attracted, the electrons in the orbitals are attracted to the nucleus in a way that differs depending on the shape of the orbital. Some orbitals have more penetration to the nucleus, and so what you see is that the sigma 2p drops rather dramatically and eventually goes below the pi 2p, starting with oxygen here. Everything kind of goes down as we go across because all the orbitals are there. But so there is different MO diagrams for different things. And I will point out that in both of these MO diagrams that you're looking at here, they're ignoring the fact that there is a sigma 1s and a sigma star 1s underneath all of those. So that applies all the way across and underneath this one as well. They're just ignoring it because it's full. So if you look over here to the right, this is oxygen. This is taken from an example in our textbook. This is figure 540. So again, we have our oxygen atom here. We have another oxygen atom over here. Oxygen's 1s2, 2s2, 2p4. We've left the 1s electrons out because we know that they cancel out. Down here at the bottom, we would have, 1s with 2 electrons and a 1s with 2 electrons. And then we have lower a sigma 1s that's bonding and a sigma star 1s that's anti-bonding, and those are filled, and we just leave them out because we know they're filled. Move that up just a smidge. Okay. So what's interesting about this one is if you then count up your bonding and anti-bonding, and this is the bond order calculation of O2. Counting the ones above in the diagram here, we've got 2 bonding and 6 bonding for our 8 bonding electrons. Then we have 2 that are anti-bonding and another 2 that are anti-bonding, counting that one. And again, if we use this one down here, we would be saying 10 minus 6 over 2. So 8 minus 4 over 2 is 2. 10 minus 6 over 2 is also 2. That's consistent with oxygen's Lewis dot structure, which looks like that. So that's our valence bond theory model of oxygen. So it is consistent. Again, the only difference between the bond order in the printed thing, which is 8 minus 4, and the bond order that I wrote in red below there, is that in the one in the example, they ignored the presence of the sigma 1s and sigma 1s star electrons, which cancel out. And down here, I did the calculation with both of them there. The thing that this predicts, though, is that that's different from valence bond theory, is that oxygen has unpaired electrons. Now, this solves a problem that valence bond theory doesn't explain about oxygen. If you have unpaired electrons, that means that you are paramagnetic. Which means that you're attracted to a magnetic field. And it turns out that if you have liquid oxygen, and there's an image of this in the book, if liquid oxygen is exposed to a magnetic field, you can see a deflection of your stream of liquid oxygen, that it's attracted to that magnetic field. The opposite of paramagnetic, hydrogen up here, which has got all paired electrons, is diamagnetic, which means all electrons are paired. And that means that you're very slightly repulsed by a magnetic field. And there's actually a kind of a cool experimental device to tell if something's diamagnetic or paramagnetic. It's called a magnetic susceptibility balance. It's simply a balance that has a magnetic field set up around it. And then you weigh it, turn the field on, and see whether the weight goes up a lot or goes down just a teeny bit, I think is the way it's usually oriented. And if it goes down a teeny bit, it's diamagnetic. And if it goes up a lot, it's paramagnetic. And the more unpaired electrons you have, the more the weight changes. Over here in table 5.2, you have a electron configuration written for these homonuclear diatomics, and you have the bond orders here. The electron configuration, again, is for just the outer electrons, and this would obviously correlate to this diagram. So lithium, for example, lithium has 1s 2 and 2s1, so our 1s electrons fill those sigma 1s and sigma star 1s, and then what we're going to have up here is a single electron. No, we're going to have two electrons because we got a 2s, 1 electron on both of the lithiums. And when we do the bond order calculation, we get 2 minus 0 or 4 minus 2, however you want to do it. That comes out to be 1. So you might go through here and confirm these bond order calculations, but this says that the dilithium molecule is theoretically stable, has a bond order of 1. If you try to put beryllium together and make Be2, you see that it has a bond order of 0, and a bond order of 0 corresponds with the experimental finding that beryllium-2 is unstable. And you see also that there is no such thing as Ne2, and that's confirmed by the bond order of 0 there. So make sure you could read these and recreate those calculations. So I do want to just show you how it can be applied to bigger molecules. Benzene is a molecule that you'll see a lot in organic chemistry if you haven't seen it yet. It's a cyclic 6-membered ring of carbons with alternating single and double bonds, and each carbon has a hydrogen on it, so they're all sp2 hybridized. So quick, how many pi and sigma bonds have I got there? We have, I'll pause now if you want to work that out. We have 3 pi and 12 sigma. Each carbon has a sigma bond to a hydrogen and a sigma bond to another carbon, and not, if I just count one of those, then I don't double count the carbon-carbon bonds, I'll wind up with 12 sigmas. So what we do a lot of times is we treat the sigma bonds using valence bond theory, but we treat these pi bonds using MO theory. And those pi bonds don't behave in benzene like their 3 separate pi bonds. There's a phenomenon called resonance that we talked a little bit about that goes on and makes benzene a very stable thing. So frequently those are treated in MO diagrams. So this is an MO diagram that I pulled from the web of the molecular orbitals associated with simply the double bonds, or the pi cloud we call it, in benzene. And you can see that we get 6 molecular orbitals, and if you look at the drawings of the p orbitals on the ring there, you can see these are all in phase. And then up at the top, they're all out of phase. As you go from 1 to the one next to it, the phase always changes. So the all out of phase is the least constructive or the most destructive overlap of those orbitals, and that's the highest energy. Anyway, so I just want you to be aware that you might see MO diagrams coming back into play, and they're not always very good in organic chemistry, saying, wait a minute, we're going to treat the sigma structure as VBT, and we're going to talk about the pi bonds as MO diagrams. They kind of expect you to pick up on that. So I want to briefly talk about coordination compounds and complex ions, and that is the chapter 19 is where we are there with that. So this is something that is, I think, about the only chance you're going to get to hear about this in your education. So I did want to mention this. So the transition metals, this inner block here, this is the transition metals that are called the inner transition metals. And then down here, these lanthanide and actinides are called the outer transition metals. The way these things form compounds is a little different. First of all, I want to talk a little bit about what kind of things you form. So typically these ions form positive, these metals form positive ions. And if you look at the first row here, it's pulled out. So this first row is pulled out over here in this next figure, and it just shows you some of the common ion charges that you might have with those. Now, that's hard to predict. You can kind of rationalize these sometimes, but the rationalizations don't always hold out. But not a bad idea to know some of these, but I wouldn't necessarily commit them to memory. One thing that we talk about with coordination compounds and complex ions is something called the 18 electron rule. And the 18 electron rule basically says if you take the d electrons on the metal plus the electrons donated by ligands, which we're going to explain what those are, that for most stable things is going to be equal to 18. Now, so this is kind of like the octet rule for these kind of compounds. And if you count the boxes across the periodic table, you know, if you go from here all the way over to there, that's 18 boxes. That's where it comes from. It's filling up essentially filling up the lowest energy level orbitals. These have a much more complicated MO diagram. We'll talk about that a little bit later. This rule, though, is just not nearly as hard and fast as the octet rule, and of course, you know, the octet rule has some exceptions. 16 electron complexes are quite common, and there are other ones. One trick I want to show you in terms of figuring out the d electrons, if you look at the atomic number on the top of the first row of the periodic table in the transition metals there, that atomic number, ones place, equals the number of d electrons in the atom and the +2 ion for that compound. So the iron atom, for example, is argon 4s2 3d6, and I got that 6 from that 6 there. And that's, you know, just because it happens, it starts with 1 and that happens to give me the number. If I did iron plus 2, well, what happens when transition metals ionize is that the ns orbitals go up higher in energy, and it will be empty, and we're losing 2 electrons to be the 2+ ion. So essentially, those electrons get taken away first. So what we have here with iron plus 2 is argon 3d6, and the 4s orbital, which is now higher in energy, has 0 electrons in it. If I want to think about iron plus 3, well, that's argon 3d5, because I just have to get rid of 1 more electron. So iron plus 3 is the same electronic structure, for example, as manganese plus 2. And the nice thing about it, of course, is I can go to something like, say, ruthenium here, and say that ruthenium plus 2 is going to have a end in a 4d6 thing, because iron ends in a 4d6. And again, I'm not using the 4 and the 44 atomic number of ruthenium to get that. I'm using the 6 and the 26 of iron, which gives me the number of d electrons in that column. So you can fairly quickly count the d electrons if you know what the atom is and what the charge is. I've got some depictions here, again from your textbook, of some complexes, and we'll maybe practice doing some of the calculations for these. So this first one here, you see the brackets there with a plus charge outside. That tells us it's a +1 ion. And you may recognize that we have an ammonia to the left and the right of the silver. Oftentimes the ligands are neutral molecules. So ammonia is neutral. So if I think about the metal here, silver +1, so silver is over here in column 11, which is under 9 for copper. The silver +1 means that silver is D10. Silver +2 would be D9, silver +1 is D10. The ligands, I have 2 ammonias. They're each donating 2, so that's 4. So this is a 14 electron complex. And like I said, the 18 electron rule is not carved in stone as much as the octet rule is. Now, if I come over and look at copper, this copper chloride complex, CuCl42-, the next one, the chlorines are all considered to be negative ligands. So I have 4 chloride ligands times 2. That's 8 electrons. And then for this to be -2 overall, copper has to be +2, right? If this is negative and that's negative and that's negative and that's negative, that'd be -4. If copper is +2, then the whole thing's -2. So copper +2 is D9. So 9 + 8, that is a 17 electron complex. And again, that's you know, a little strange. It's not an octet rule type compound. I would predict that the maybe the CuCl43- might be, I'm sorry, CuCl4, yeah, right, 3- might be even more stable, because if I had copper +1, it would be D10. It'd be an 18 electron complex. Last one over here, we have 6 waters as our ligands. So those H2Os are waters times 2 each. That's 12 electrons. And then our cobalt, water's neutral. So our cobalt is +2. And cobalt +2 has 7 electrons. So this is a 19 electron complex. Again, probably not as stable as the cobalt +3 18 electron complex, but those are examples of some complexes, and you can see some of the geometries. I found online, this isn't in your book, a table of some of the common ligands, and what I wanted to point out is whether they're charged or not, which is listed here, how many electrons they typically donate. So all of these guys here typically donate 2 electrons. So do these two. Oxalato here which is the oxalate ion, it usually donates 4 electrons. Amine, water, nitrosyl, carbonyl, dioxygen, dinitrogen, those usually donate 2 electrons each. Pyridine is going to typically be 2, but it could be more. And ethylene diamine typically donates 4, and we'll see some pictures here. So figure 1915 talks about the ethylene diamine ligand, and the shortcut name for that is we just call it EN for that. So if you look at this molecule, let me get the highlighter and show you this. So this is one ethylene diamine molecule here, and you can see how it's connecting to the cobalt twice, and that's referred to as biting it twice. And so the typical name here is that we'd say this is a bidentate ligand, which again goes with that 4, occupies 2 coordination sites. All of these are monodentate ligands, which means they only occupy 1 coordination site. They donate 2 electrons. So dentate from biting the metal, and then how many times it does. And of course, the things that are bonding to the metal here are these lone pairs. That's where the electrons come from to bind to the metal. Here is a real beaut of a ligand. This is the heme ligand here, and I'll draw this around here, this whole thing. And you walk around with a big supply of this because it's in every hemoglobin molecule in your body, and hemoglobin, I think, is something like 97% by mass of the red blood cell. So that whole thing that I've highlighted there, everything except for the iron, is a ligand. And so if I ask you to classify it in terms of its dentateness, what would you come up with? So there's 4 places where it bites the ligand. So this is called a tetradentate ligand. And again, this is extremely important. The heme molecule is also involved in other proteins in your body, the cytochromes that are in the electron transport chain. There's a very similar to heme ligand that's involved in the chlorophyll and photosynthesis in plants. Some fascinating stuff there. One thing that you might note is that if you look at the nitrogen, the nitrogens are a little different. So this nitrogen here and this nitrogen here are different. They've got 4 bonds, and this nitrogen here and this nitrogen here only have 3. So the nitrogens in the redder color are donating the lone pairs. The nitrogens that are in the green color are donating a sigma bond. Essentially, so it's a little different there. The whole heme ligand is considered to be a 2- ligand, and the iron is a 2+. So iron 2+, we would say, is D6. Heme is donating 8 electrons, so we're talking about a 14 electron complex. What happens is that another pair of electrons comes from amino acid underneath it and binds the iron, and then oxygen binds the iron. So amino acid, which has a nitrogen, that's 2 more, and O2 gives us 2 more. And so in hemoglobin, and I should preface that in oxygenated hemoglobin, it's an 18 electron complex. The shapes are a little more complicated. It's a little harder to predict, but it's very common, for example, to have a 6 coordination number, which is how many spots the pairs of electrons are donated at. A 6 coordination number octahedral. It's very common to see 4 coordination, either tetrahedral or square planar. We can do a little bit of predicting based on the number of d electrons, which way it's going to go with tetrahedral or square planar. But those are some examples of complexes there. Here's an example of the tetrahedral or square planar. Zinc with 4 cyanides. Cyanide is a -1 ligand. There's 4 of them. So that's going to be 8 electrons. Zinc is, if the cyanides are all -1, then I've got to have zinc be +2 for this to be -2 overall. And if I go back and look on my periodic table here, zinc ends in 0, which means we have 10 d electrons in the +2. So this would be a d10, and that would give me 18 electrons there. And that says tetrahedral is oftentimes associated with 4-coordinate D10 molecules. And again, the fact that there are 4 cyanides is what we mean by 4-coordinate. To the right here, we have cis dichlorodimenoplatinum 2. The chlorines are -1 ions. There's 2 of those. That's 4 electrons. The amines, there's 2 of those. They're neutral. That's 4 more electrons. So the platinum, if the chlorines are -1, and there's 2 of them, and this whole thing is neutral, there's no charge, so platinum must be +2. So if I go back to my periodic table, platinum is in the group that has 8 d electrons if it's +2. So that's D8, and so we have a 16 electron complex, which is square planar. And again, you see up there the square planar is associated with that D8 thing. You can have isomers here. This one is called cisplatin, and it's one of the anti-cancer drugs that gives you the most side effects. There is another version of this where you have your chlorines opposite each other, and this is again a flat plane. We've got the bonds in the back will dash. They're going away from us. Oops, wrong way. Dash is there. I usually write my neutral lone pairs there to show them. So this would be called transplatin, and that's again a kind of a common name for it. Cis and trans are usually underlined. You will use those in organic chemistry a lot to talk about isomers, right? Those are isomers. Okay. We have some more isomers here in figure 19.1. If you have cobalt with 4 waters and 2 chlorines, if the chlorines are next to each other, that's the cis form, that compound gives you a violet color, a purplish color. And then if the 2 chlorines are opposite each other, that's the same molecule except a different arrangement of the atoms, so it's a different isomer. And that one turns out to be green. So you can see the difference sometimes, not only in the sort of chemical reactions they do, but also in properties like color. One thing a lot of folks are attracted to transition metals is because they tend to be pretty colorful. In terms of cisplatin and transplatin, cisplatin, like I said, is an anti-tumor drug that binds the chlorides, basically hydrolyze away, and that binds to nitrogens on DNA and stops DNA from copying itself, which of course would stop a cancer cell from growing. It also stops normal cells from growing and dividing, and so that's why you have side effects. Transplatin, because when those chlorides dissociate, they're opposite each other, isn't as effective, although it might be reasonable to expect it to maybe rearrange a little bit when it's in the system. But I don't think transplatin is as an effective a drug as cisplatin. Now let's talk a little bit about the orbitals and what's going on with those. So in figure 10.3.3, you have the d orbitals down here. You've got the dx squared minus y squared orbitals, which has lobes on the x squared and y squared axes, and nothing on the z axis. Then you have the dz squared, which has a component that's on the positive and negative z axis, and then an annulus that's in the xy plane, or centered in the xy plane. And then you have 3 sets of orbitals for every plane there. You've got the YZ in the YZ plane, the XZ in the XZ plane, and the XY in the XY plane. So they all have different shapes. And when you think about your ligands, which they're representing by these L's here, when those ligands come in and the ligand orbitals interact with the d orbitals on the metal, the orbitals interact with the ligands differently, and they interact differently depending on how many ligands are coming in. So this is looking at the octahedral case, where you've got a ligand coming in on each axis, basically from the positive and negative end of each axis. And as they interact with those orbitals, you have the d orbitals go down in energy. Some of them go down in energy more than others as they're interacting. Or we might actually, I think we usually think of it as the ligand orbitals going down and the d orbitals moving up. And what happens is you get a splitting in those d orbitals. So instead of having 5 d orbitals all at the same energy level, we now have a split between what we call the T2g orbitals, which are the ones at the bottom, and the EG orbitals, which are the ones that go up in energy. And the difference between those is called delta suboctahedral, or delta zero. And the size of that difference and the number of electrons that are in the d orbitals influence frequently the color of the compounds that we see. So this is a representation. Again, we're just focusing on the d orbital part of the MO diagram because the MO diagram is quite complex. So just like with benzene, where we only looked at the pi bonds. Here we're only looking at the d orbital part. So if you have iron 2+ with no ligands, all 5 of the d orbitals are at the same energy right here. If I have a complex of iron 2 that has 6 water molecules, then they split a little bit, right? And but if I go all the way to iron +2 + 6 cyanides, they split a whole lot more. What happens here is that basically in this case, which is called a high spin, the difference, there's an energy associated with pairing electrons. And what happens in high spin is that the energy to pair is greater than the splitting energy. In the low spin situation here with the cyanide ion, that splitting energy is now greater than the energy to pair, so it's easier for the electrons to pair up in the lower T2G orbitals than it is to go to the higher ones. And of course, this one would be paramagnetic. This one would be paramagnetic. But the iron cyanide complex is going to be diamagnetic. Now, the low spin and high spin cases can be tracked by talking about something called the spectrochemical series. And chemical series, spectra, talks about the basically what we see when we're measuring the light that's absorbed or emitted by these things. So what this suggests is that most intense light that's absorbed and which light passes through changes as we do those. We talk about these as having high or low field strength. The high field strength, right, gives us the big splitting, and low spin, the lower field strength, can give us the smaller splitting and thus higher spin. And if you look at a couple of examples here, here we have 3 complexes of nickel 2+, and 1 complex with water gives us a smaller splitting and a kind of a greenish color, which is, if you think about the energy spectrum of light, so low energy, low frequency, high wavelength, are associated. So this would be, yellow, orange, red, green, blue, indigo, violet. So going this way is higher energy, right, and lower wavelength. So what you see is the splitting is smallest. We have a longer wavelength and a color that is lower in energy. From the second one, okay, so that one is that one, this one would be that one, and then the violet's way out here. So as our field strength goes up, and again that En there is the ethylene diamine ligand, what we see is that splitting gets bigger, and the energy, to basically, if a photon is absorbed by this, it's going to absorb a photon. If you think back to the Bohr model of the atom, what you're looking at is that basically, if I have my low orbitals and my high orbitals here, and I've got them filled in like this. So if I hit this with a photon, h nu, that exactly matches that difference, what's going to happen is that's going to give an excited state where an electron's been knocked up to the top level, and that will decay back down and give off similar light. So this relates to what kind of light gets absorbed and reflected by this, so we can associate that electronic differences with color. So hopefully that's going to be enough to let you tackle some of the problems associated with the transition metal complexes and the molecular orbital theory, as well as the valence bond theory.